All right, so remember what we had. We had f of x, and I get to draw really big this time. F of x equals the square root of x, and g of x equals x cubed. Now, this one's fun. Got to give myself enough room. Here's the square root of x. Here's x cubed, right? So this is root x. This is x cubed. Now we're going around the y-axis. Y-axis rotation. Let's see what that entails. Okay, let's draw ourselves a sliver of, crud, this is going to get a little bit ugly, isn't it? Now, look at my action. I'm going around the y-axis, so my sliver is going to look like this, isn't it? Ugh. Remember what happened before when my sliver of action looked like this instead of lengthwise? Well, what I needed was, let's look at this, I need an outside radius this way and an inside radius this way. So this is going to be my big R, and this is going to be my little r. But those are horizontal distances, which implies what? It implies I need functions of y rather than functions of x. Now, this is where it gets fun. This is true if and only if, now, you ready? Y equals x cubed if and only if x equals the cube root of y. Hopefully you all agree. Root x equals y if and only if x equals y squared. You with me? Now, let's look real close. Which is bigger if we're talking about a function of y? Well, clearly, look. Do you see which one's bigger? Is it going to be this guy or is it going to be this guy? Well, it's going to be this guy. It's further right. So the outside radius is going to be the cube root of y. The inside radius is going to be y squared. And then I just build it like I always would, except we got to be real careful here. This is no longer delta x, is it? It's delta y. So let's do the volume of the ith interval. It's going to be pi times the integral. Now remember, these are actually pretty convenient because this is 0, 0, and this is still 1, 1. Notice I need limits on y. Had this been 1, 2, I would have to integrate from 0 to 2, again, limits on y, rather than from 0 to 1. You'll get into problems like that down the road, but for now I just want to kind of keep it simple. I'm going to go from 0 to 1, these are limits on y, of outside radius, which is the cube root of y squared, of course, minus inside radius squared, which is y squared squared dy. I guess I didn't find I found the overall volume, didn't I? So let's erase the v sub I, and what I should do is up here, let's do the quick volume of the ith. Wow, what just happened there? V sub I is going to be pi times, and then it's going to be cube root of y sub I squared minus y sub I squared times delta y. That's the volume of the v sub ith. Sorry, you guys. Okay, now let me erase this. This looks terrible. Now let's actually do this problem out. And here's why. I often have students say, well, Ripley, wait a sec. Shouldn't this be exactly the same volume as over here? I want you to think about that. Will this be exactly the same volume? Well, let's check it. Let's do the math on it and see what we get. I'm simple country folk. You guys know this by now. So I'm going to have to rewrite this thing as the integral from 0 to 1 of, let's see, this is going to be y to the 2/3, right, minus y to the 4th dy. So this is equal to pi times, let's see, what is that? It's going to be 3/5 y to the 5/3, right? If I had to check it, I could. 5/3 minus 3/3, 2/3, that's always good, right? Minus y to the 5/5 from 0 to 1. So this is pi times, well, anything, 1 to the anything is 1, right? So I get 3/5 minus 1/5, which is 2 pi/5. They're different. Now the reason that is because the amount of time that this, or the amount of space that this region right here fills. Think about it this way. Let me do this really easily for you. If I keep it as simple as possible, if I take this gigantic sliver right here and I wrap that through 360 degrees, I'm going to get this puck-looking thing, right? And that's going to have a specific volume, right? If I take that exact same sliver and I wrap it through 360 degrees, I'll end up with this open cylinder, right? Well, think about that. Which is going to have more volume theoretically? Well, one of them is this guy might, because it looks like he kind of spends more time in space going around the y-axis than this guy. In other words, these little slivers in here don't spend very much time in space. So what ended up having, let's see, 2/5 of pi, which one has more volume? 2/5 and 5/14. 2/5 is what, greater than 5/14? Would you say that? Yeah, 2/5 is 0.4, 5/14 is about 0.3, right? Maybe a little, they're close, but they're not the same, all right? So this is a little bit greater than 0.33, probably about 0.35. All right, so this guy ends up having more volume than the other guy. Again, this is washers. Why is this washers? Easy. Notice there is a hole. See this right here? All of this area right in here, there's a hole between the action, here's my action, and this is the hole. We've got a hole between the action and the axis of rotation, and therefore we're going to have washers. So, to recap, because I know this stuff gets confusing. We're going to spend lots of time on this, so don't panic. All right, to recap, I'm going to use disk method. The disk method is when there is no hole between the action and axis of rotation. Okay, and you'll end up with the volume is equal to the integral from a to b, let's stick our pi out in front, of r, that's just our radius, squared, dx, or pi times the integral from a to b of r, let's call this r of x, right, squared, and this is going to be r of y squared dy. I should do this a little bit cleaner. Sorry about that, you guys. Now, we got to be careful. A and B, these are going to be limits on x, and A and B over here are going to be limits on y. The easy way to always check that, sorry, change colors, is remember, if it's a dx, it's got to have limits on x. And if I have limits on x, then this has to be a dx. If it's a dy, I have to have limits on y. And if these are limits on y, then I have to have a dy. In other words, I have to have a function of y. That's a really good way to check that. Now let's talk about washer method. Washer method. All right, when there is a hole between the action and axis of rotation. So always, just like I've been preaching ever since we've been in this chapter, draw yourself a slice of action. Then ask yourself, when I take this thing through 360 degrees, do I end up with a hole, right? And that's, if I've got a hole, then I use the washer method. All right, so the volume is going to equal pi times the integral from a to b of the big R, remember, big radius, squared minus little radius, squared dx. Again, a and b are limits on x. I won't write it again. Or, if I need to do these as functions of y, if it's more convenient, a and b of r of y squared minus little r of y squared dy. All right? All right. Hopefully that was helpful. Now, in the next little segment, I'm going to jump to a new technique that's called we're going to use what's called the shell method. All right? So I'll meet you in the shell method here in just a little bit. Play with these. We got lots of time. Don't panic, and I'll see you soon.